The Parker Solar Probe, the fastest object ever made by human hands, serves the solar winds at more than 630,000 kilometers per hour. That's more than 500 times the speed of sound on Earth. Its mission? To touch the sun, and ideally to avoid melting in the process. It achieved this goal in 2021 when the probe flew by Venus and skimmed through the corona, the sun's outermost atmosphere. Since then, it's carved a closer and closer past, revealing extraordinary detail about the star in the process. On its closest approach, it's projected to cross within 8.8 solar radii. That's less than 4.5 sun lengths away from the solar surface, and it will endure temperatures of 1,500 degrees Celsius. But there's a limit to just how close Parker can get, and there are questions scientists can't answer without probing even deeper into the solar atmosphere. Among these mysteries is the astonishing fact that the solar surface is actually much cooler than the outer corona. Above the solar surface is a thin 100 kilometers layer known as a transition zone, where temperatures dip from scorching 500,000 degrees Celsius to a relatively cool 8,000 degrees. While physicists have theories on how the transition zone forms, we won't know for sure until we can make closer observations. Further, some scientists predict that if a spacecraft could fly within about 3 solar radii from the sun's surface and fire its rocket at just right time, it could use the sun's gravity to slingshot itself into the outer solar system. This daring flight path, called the overt maneuver, could propel a spacecraft past Pluto in just 3 years, a trip that currently takes around a decade. But probing deeper into the corona without melting, exploding, or falling directly into the sun is a monumental engineering challenge. The first challenge is directing the probe's path. A probe falling directly towards the sun will likely pick up so much speed in descent that it either crash or be flung in the opposite direction. To avoid this, the Parker Space Probe made a series of complicated orbital maneuvers around Venus. Using the planet's gravity as a brake, it could readjust its orbit and get incrementally closer. But these country orbital tricks can only get us so far. As for the scorching heat, the Parker probe used a strategy that is not unlike sitting under a beach umbrella. Its instrumentation is packed behind a heat shield just 4.5 inches thick. One side is made of highly reflective white ceramic that scatters much of the incoming sunlight. The other side consists of carbon foam, sandwiched between two layers of carbon, further reinforced with carbon fiber. The foam is around 97% air, so it acts as an insulator, not allowing much heat to flow through. The outer carbon panel is very dark and can withstand high temperatures, so it efficiently absorbs any remaining heat and radiates back out to space. A sensor system constantly adjusts this shield to ensure the craft instruments remain in its shadow. But Parker's heat shield can only get so close. To get even closer, one possibility would be to ditch the heat-absorbing carbon materials entirely and double down on deflection. Researchers at NASA's Innovative Advanced Concept Program have developed a novel ultra-reflective coating called solar white that's predicted to reflect 99.9% of the sun's energy. They plan to use solar white to coat an outer curved umbrella-like shield. Then, a second conical shield made from a silver A second conical shield, made from a silvered reflective material, would shunt away any remaining radiations that escape through. With both novel shields, scientists believe they could serve a probe as close as 2 solar radii from the surface, but we won't know for sure until these materials are further tested. At these close distances, we might unlock the mystery of transition zone. We may learn how to better predict solar behaviors like flares and geomagnetic storms, which put satellite and our communication system on Earth at risk. And we get unprecedented look at our star, and perhaps one day, with the sun's assistance, at our most distant neighbor.